Hello everyone. Today we are going to discuss about magnetic effects of electric current. So yes, as you can see here in the image, when the wire is carrying a current, it will have the magnetic effect around it. So for different types of conductors, how the effect is seen, that we are going to discuss in this video. So these are the topics that we are going to talk about: concept of magnetic field, then magnetic effect of electric current with the help of Oersted's experiment, different rules in order to figure out the direction of magnetic field, Biot-Savart's law, vector form of the law, and the concept of permeability, followed by the board questions based on this topic. So let's begin. Firstly, to understand the concept of magnetic field, we need to understand that all of the magnetic phenomena, they actually come into result from the forces between electric charges in motion. Yes, when we observe the free electrons moving through the conductor, we say that there is a current passing through the wire. The motion of charges through the conductor, they constitute a current, right? So in order to introduce this concept of magnetic field, we need to discuss this interaction between the charges in following two stages. The first stage over here is the moving charge, which sets up the current in the wire. It also creates a magnetic field in the space surrounding the conductor. The second stage over here is the magnetic field. It exerts a force on a moving charge or a current in the field. So this will be the kind of second part of this chapter, wherein we'll be talking about many different examples with the help of a famous rule called Fleming's left hand rule. Before that, we'll be talking about magnetic field produced because of the moving charge or the current for different types of conductor, maybe a straight conductor or a conductor wound in a form of a loop. So similar to electric field, magnetic field is also a vector quantity, and it is denoted with the symbol B, capital B, and a bar sign on top of that represents that magnetic field is a vector quantity. Now let's understand the experiment by which firstly we got to introduce with this particular effect. So the physicist named Hans Christian Oersted has been credited with discovering the link between current and the magnetic forces. So back in 1820s, he was giving a demonstration of battery when he noticed that a compass needle lying on a table was actually responding when he turned the electricity off or on. So over here besides this image, you can see here, once we close the switch, the current will start passing through the wire, and besides that, whatever compass needle is placed over here, that will start deflecting. So let's observe this in the proper experiment out there. So here you can see that the arrangement made over here, such as the compass needle is placed just below the wire, and when we close the switch, the current will start passing through the wire in this way. As soon as the current passes through the wire, the compass needle will deflect something like this towards the left. On the other hand, if I reverse the direction of current, that means if I'll reverse the direction of the battery polarity, if I'll change it, then the direction of current will also reverse, which will in turn reverse the direction of the deflection of the compass needle as well, which actually tell us that yes, magnetic field is a vector quantity. By the deflection of the compass needle, we can actually recognize that it is deflecting and responding to the current in the wire. Okay, so now let's understand the rules by which we can actually figure out the direction of magnetic field. So the first rule that we have over here is Ampere's swimming rule. Yes, so if you look at this image over here, in order to understand and apply this rule, we need to imagine a man who's swimming in the direction of current from south to north. Okay, south to north facing a compass needle kept under him such that the current enters his feet. So here you can see the current is entering through his feet, and this is where the compass needle is placed under him. So when we imagine a current entering his feet, we observe that the compass needle will deflect towards his left. That means towards the west. So this is how we can figure out the direction of magnetic field by using Ampere's swimming rule. Now the most common rule that we use in this chapter is right hand thumb rule. So yes, since it is a right hand, first you need to stretch the thumb of your right hand in the direction of current passing into the conductor. So let's say right now in the image, as you can see, current is passing in the vertically upward direction. So we stretch the thumb of our right hand in the upward direction. The remaining fingers, remaining curled fingers of this right hand over here, the way they are being curled, that represents the direction of magnetic field around this wire. So over here we understand that magnetic field around a straight conductor is observed in the form of circular lines. So at the bottom, the circular line, the curve that you see over here, that actually represents the magnetic lines of force. This is magnetic line of force. And if you see, there is a dot over here. Just show you. Yeah. So if you see at the bottom, there is this curve line shown over here, which is representing the magnetic line of force, and the arrowhead represent the direction of magnetic field. So if the current is moving in the upward direction, the magnetic field is kind of in an anti-clockwise direction. So this is how, by using right hand thumb rule, we understand the magnetic field around a straight conductor. Let's move ahead and talk about the important law over here, which is known as Biot-Savart law. So for this particular law, what is it all about? With this law, we are going to find out the magnetic field, the small fraction of magnetic field. We got to know that the symbol for the magnetic field is capital B, but out of that, right now with the Biot-Savart law, we are going to find out only small fraction of that total magnetic field. Why this is so? Because if you see the green colored line over here, that represents the conductor through which the current I is passing. Okay, but out of this entire conductor, we are going to imagine a small element of that wire. So that small element, we take it as a length dl. Rather than considering the entire length L, we'll be considering the dl over here. So this, since this dl is carrying current I, together we call it as current element. Children, we know current is not a vector quantity, it is a scalar quantity, but IDL bar together is a vector quantity because the length of the dl is taken in the same direction as that of the current. Now for this particular current element, we are trying to figure out that around this current element, how much magnetic field it will possess. So here we'll have our point of interest, which is point P, as you can see over here. And this point P is at a distance R bar, at a distance R from the current element. And if you look at the orientation of this point P, the point of interest, is from DL to point P is in this way. So the angle theta that you can see over here, angle theta is in between the two vectors. Which two vectors? Vector dl bar, basically idl bar, and vector r bar. So what is r bar over here? This is actually the position vector of point P. Where point P is located? It is located at distance r from the vector dl. Okay, and its orientation is angle theta. Since it is placed at distance r over here, now let's understand the statement of the law. So in order to find out the strength of the magnetic field dB, we have these statements. Few proportionalities are there. So the first proportionality is the strength of the magnetic field is proportionate to the current I passing through the element, small current element. Same time, dB is proportionate to the length of the current element, that is dl. It is proportionate to the sine of the angle theta. Angle theta is the angle in between what? In between the two vectors, current element IDL bar and R bar, the angle between these two vectors. And it is inversely proportionate to the square of the distance between the two things. Which two things? The current element and the point of interest. See, you can imagine your point of interest anywhere, somewhere here, or maybe closer to the wire. But that way, as per the distance and as per the orientation of the point of interest, the amount of magnetic field it will have at that location would vary, right? So that is why we need to combine the whole thing with reference to this law. So combining this entire proportionality, the relationship would look like this, that dB is proportionate to IDL sine theta over R squared, right? Now every proportionality has a constant of proportionality that we know. So over here the constant of proportionality is mu naught over 4 pi. So mu naught, what is this mu naught known as? This mu naught is known as permeability. Yes, you heard me right. It's the ability. Ability to do what? It's the ability to permit that medium to get magnetized into that particular external magnetic field. We are going to discuss that in detail further. As of now, let's understand the value of this constant. So every proportionality constant has a fixed value. Over here, 4 pi is just a numerical constant. Mu naught has a value 4 pi times 10 to the power negative 7. And the remaining variables are as it is. Now, in the diagram, of course, you're looking at this cross on the right hand side and this dot on the right hand side. So let me tell you about this point P dash. What is this P dash? P dash is the same point, is the point which is at the same distance away from the current element but on the opposite side. Okay. Now let's understand the logic behind this dot and the cross. So to understand that, we need to look at the vector form of Biot-Savart's law. So what is a vector form? Vector form, we write that we try to understand the direction of the magnetic field as a vector. So dB bar would be written as the proportionality constant as it is, and here the two vectors. So you can see a cross over here. So yes, it is a cross product. Okay, so in cross product, children, you might remember in grade 11th you have learnt cross product is always written as with the help of a sine theta. So if I have, let's say, a bar cross b bar, I will write this as ab sine theta. So what is this theta? Theta is the angle in between these two vectors. So right now over here we have these two vectors. I have dl bar cross r bar, but right now we have a r cap over here. Now r cap is what? It is the unit vector in the same direction as that of that r bar itself. Now how do we write the unit vector? We write the unit vector as the vector itself upon its magnitude. So this one additional r is added over here and the denominator becomes r cube. Okay, so in the numerator you can see here that there is dl bar cross r bar. So whenever you will write the vector form, you will write r cube in the denominator and there will be no sine theta into picture because we are writing the vector form, vector notation. But when you will write down the magnitude, for magnitude you need to stick to this formula. dB is equal to mu naught IDL sine theta upon r squared. Okay, 4 pi r squared. So mostly while solving the numericals, you are going to use magnitude formula. Now here is the understanding for mu naught, children. Mu naught. Now mu is the symbol for permeability. When I'll put this naught over here, this tells me that this is the permeability of free space. Okay. You might remember the symbol used in electrostatics, that was epsilon naught. What was that? That was permittivity of free space itself. Okay, so permittivity we use in electrostatics, whereas permeability we use in magnetism. Okay, now let's understand what exactly is this permeability. So it is the measure of magnetization produced in a material in response to an applied magnetic field. So let's take an example of soft iron. soft iron core, or for that matter you might have heard about the word armature. Armatures are mostly made up of soft iron. So soft iron is a material which has high permeability. What does it mean? High permeability is the ability of soft iron to get magnetized easily into an external magnetic field. Suppose I have this soft iron rod and I'll keep it into some external magnetic field, so it will get magnetized very easily. That way we say the permeability of soft iron is high. Now let's take an example of steel rod. If I have the same measure of steel rod and I'll keep it into magnetic field, then it will not get magnetized that easily. So we say steel has low permeability. So what is permeability? It is the ability, it is the measure of getting magnetized into the external magnetic field. This is the ability property of a given medium or given material. Okay. So that is it about the permeability. Let's move ahead. Here we discussed about Biot-Savart's law, its magnitude and the vector notation. Now let's move ahead and understand the direction and the logic behind dot and cross. So direction of dB bar is same as that of dl bar cross r bar, because we understood, children, previously as with reference to cross product, we know one thing. When I write a bar cross b bar, yes, of course, the magnitude is found out as AB sine theta. What about its direction? The direction is given with a vector n cap. What was this n cap? N cap is the unit vector which is lying along the direction of the product vector. So the product vector, the direction is given by the right hand rule, and that depends on the angle theta, the way you rotate your hands. So since it is a right hand, you need to curl your fingers with reference to the sense of rotation. So angle theta over here is the angle in between these two vectors. In our case, for Biot-Savart law, it is the angle in between dl bar and r bar. So the angle is measured from vector d l bar to r bar. That's how you measure the angle. So you will curl the fingers from dl bar to r bar, and wherever the thumb is pointing, that will give you the direction of magnetic field. So here are the two exemplary images placed over here. So in the first image, if you see, this is just an example. So in the first image, if I'll curl the fingers from vector A to vector B, then the thumb is pointing in the upward direction. So here the thumb is pointing out of the plane of this paper. So let's imagine this is the paper over here. So the two vectors are in this plane. So the vector, the product vector will point out of the plane of paper. So this will be represented with a dot. Why dot? Because when you will look at the top view, when you will look from here, you're going to see the tip of this vector. So we represent that with a dot. On the other hand, if you have to curl your fingers from vector B to vector A like this, then your right hand thumb will point in the downward direction. So if you look at the top view over here, you will see that the vector is going into the plane of paper. So into the plane of paper, you will see the tail of this vector. You will see this tail of the vector. So that would appear like a cross to you. So wherever you will come across that the magnetic field is going into the plane of paper, will show that with a cross. So let's go back to our diagram and understand. So here on the right hand side, one thing we understood, we need to measure the angle from dl bar to r bar. So here I am going to curl the fingers from dl bar to r bar. So stretching the fingers of my right hand, where the thumb is pointing. Thumb is pointing in the downward direction. So that is going into the plane of paper. Hence we have a cross over here. On the other hand, if I look at this point P dash, so going from dl bar to r bar. So here is a dl bar. From dl bar to r bar, when I'll curl the fingers of my right hand, where the thumb is pointing? Thumb is pointing in the upward direction. So that is pointing out of the plane of paper, and that we will represent with a dot. Okay, so further in this chapter you might see some images wherein the magnetic field shown with the crosses which are equidistant, and this is how the magnetic field is shown. What does it mean? It shows the uniform magnetic field in that region going into the plane of paper. Okay, so this is the total vector based understanding for Biot-Savart law. We understood where to represent the dot. Dot we will represent when the magnetic field is coming out of the plane. Cross we will represent where the magnetic field is going into the plane. Alright. Now based on this, let's move ahead and understand the unit also. Magnetic field, we understood the magnitude for it and the direction. Now what is the SI unit? SI unit to measure the magnetic field is Tesla. Now how do we define it? What is 1 Tesla? So let's write down the formula for magnitude of magnetic field. Mu naught upon 4 pi. It is a numerical constant which will not have any unit. So IDL sine theta upon r squared. This is the magnitude. So if in this formula, let's say we have current I is 1 ampere. So mu naught, the value was 4 pi into 10 to the power minus 7. In the denominator, we have 4 pi as it is. Current I is 1 ampere, dl is 1 meter, and r is also 1 meter, and the angle theta is 90 degree. Sine 90 is 1. So here putting in the denominator that r is also 1 out there. So sine 90 degree is 1. So all together what are we left with? 4 pi and 4 pi gets cancelled out. We are left with 10 to the power negative 7. Okay. So based on this, we will define the value of 1 Tesla as a magnetic field. So 1 Tesla is 10 to the power negative 7 times the magnetic field produced by a conducting wire whose length is 1 meter and it is carrying the current of 1 ampere at a distance of 1 meter from it and perpendicular to it. The word perpendicular represents angle theta to be 90 degree. Rest everything else is 1 over here. So placing everything as unity, that is 1, we are left with the value 10 to the power negative 7, and that is how we define the unit of magnetic field as 1 Tesla. Now let's move ahead finally and solve a question. So here we have an in-text question for you children. Yeah. Here we have a current element, that is delta L equal to, so delta L, since it is a vector quantity, I'll put a vector sign on top of that, bar sign. So delta X I cap, this is placed at origin and carries a large current of 10 ampere. So let's show the current element something like this. This is delta x. Here the length of delta x is also given, which is 1 meter. Now they have given that this is placed at origin. So let's draw the xy plane out there. This is y axis. This is x axis here. Okay. And now we'll show the distances. This is y, this is x axis. The length of this delta x element is how much? This is 1 centimeter. This is delta x. Now they have asked us to find out the magnetic field on y-axis at a distance of 0.5 meter on y-axis. So this is vertically, let's say somewhere here is our point of interest, which is at a distance of 0.5 meter from the current element. So point of interest is at this distance. What do we call this distance as? We denote that distance with the symbol r. Okay. So now let's write down the things given to us. The things given are the distance r is 0.5 meter. DL is nothing but delta x over here, since it is given as equal to delta x times I cap, which is 1 centimeter. We have to convert that into standard form. So 0.01 meter. I'm going to write this as 10 to the power negative 2 meters. Further, we also need angle theta. So angle theta is always in between DL bar and R bar. So R bar is along y axis and DL bar is along x axis. So this is the angle. So how much is this angle over here? This is clearly 90 degree. So sine theta is 90 degree. Now let's find out the magnitude by using the magnitude formula. Mu naught over 4 pi times IDL sine theta upon r squared. Okay. So let's put up the values over here. Mu naught, the value is 4 pi times 10 to the power negative 7. Denominator 4 pi, if you want you can write. If you don't write, that is also okay, because that is gonna get cancelled out. So further, let's put up the value for current I. Current I is given as 10 ampere in the question. DL is 10 to the power negative 2. Sine theta, which is sine 90 degree, that is going to be 1. R squared, what is R? R over here is 0.5. So 0.5 and the bracket squared. This is important. So 4 pi and 4 pi will get cancelled out. Let's simplify this thing over here. We are left with 10 to the power negative 7 times, this will solve as 10 to the power negative 1 and sine 90 is 1. In the denominator, 0.5 squared will become 0.25. Okay. So in the numerator, I have 10 to the power negative 8 and 0.25 in the denominator. So let's do the calculations further and find out the answer for this. So 1 over 0.25, that will become around 0. Okay, we'll write this as 1 over. If I'll write this as 25, I'll have to write this as 100, and this will become 10 to the power negative 8. So what is the answer? 4 times 10 to the power negative 8. Right? Yeah. So 4 into 10 to the power negative 8 Tesla is the magnetic field because of this current element. Right? That's your answer for this. But we are not done over here, children. We still need to figure out the direction. Now, by the direction, we understand that this is a cross product between two vectors. Which two vectors? DL bar cross R bar. Your DL bar is written as delta x I cap cross R bar was along y axis. So that is some y value into j cap, isn't it? I and j, I is a unit vector along x axis and j is a unit vector along y axis, right? So over here we are taking the cross product in between these two vectors. Right now we are simplifying for the direction only. So let's write down the magnitudes on one side. So we have got I cap cross j cap. Now if you will recall from grade 11, cross product between these two unit vectors gives us the third unit vector, which is along the third axis, that is k cap. So the direction of this magnetic field will be along z axis, but that will be along positive z axis. So we will show it something like this. So along this z axis, that is positive z direction, the magnetic field will be pointing with a value 4 into 10 to the power negative 8 Tesla. This is how you should write your final answer along with the direction. The magnitude 4 into 10 to the power negative 8 Tesla, and the direction is positive Z direction. Okay, don't forget to write the direction also, which is very important. So here in today's video we discussed about the magnitude of magnetic field with the help of Biot-Savart's law. We also understood the direction with the help of dot and the cross. We understood the term called permeability, and we solved the question. So for the more videos, keep on watching for the further topics of this chapter. Thank you everyone.